So, I'm Dajun Zhang from Shanghai University, and I'm very happy to chair this session. Today, the speaker is Professor Qiao from University of Texas, Rio Grande Valley. His topic is Peakons and beyond. Let's welcome. George, you can start.
Okay.
Okay.
All right. Good morning or good afternoon. Our time is evening. First of all, thanks Giorgio for your invitation to speak at this international seminar. And also thanks to Professor Zhang, brief introduction. Okay, what I want to show today is Peakon and beyond. I put scalar form. I put down scalar form, okay, which means, not component form, okay. If I have another chance, maybe next topic would be Peakon and beyond number 2, the component form, okay. So the topic is the work I worked with Dr. Qiao. He was my postdoc some years ago. And recently, the other Professor Zhu and Professor Reyes. Reyes is a professor from University of Santiago, Chile. Okay. Now, actually, this project is one of topics in my current research program. Okay, I listed here. My collaborators currently, we have faculty from our department, Dr. Vasilin Vechev. He does a Bosnian equation with some particular solutions. And we have 4 international students, actually 5, no, let me see. 3 international students and 2 local. And one is Chinese student and is coming in the coming 4th semester. So recently, due to COVID issue, and it's hard to get a visa to come over to United States. But now it's better, situation much better than before. Yeah, he just got a visa 1 month ago. In this talk, I already introduced my collaborators. Okay, now regarding our research program, currently in my group, we have 3 directions. One of the direction is PD and inverse problem. Actually, it's for radar image reconstruction as application in radar imaging. But the basic idea is from an inverse problem of 3-dimensional Maxwell equation. Okay, yeah, in mathematics, this is the linear forward problem is a linear case, but the inverse problem is something different. Most important is under inhomogeneous media. Okay, that is for mathematics work. So application are going to use the inverse problem to do image reconstruction. Of course, the image is for radar imaging. I call the SAR and ISAR. Usually the engineering they are using Fourier transform, but in here we're going to use a Fourier integrable operator. Okay. SAR means a synthetic aperture radar. It's for the target not moving. If inverse in synthetic aperture, this also talk about the inverse. That is for the moving target. Most important recently, probably most of the audience know the machine learning, deep learning for the 3-dimensional image reconstruction, very, very useful. Okay. Those 2 works that you have to use a lot of skills in either algorithm and theory, okay, then simulation. So we have to do collaboration with engineering people, like electrical engineering, okay. Now the third topic is long time I worked in China, integrable system and solitary wave solutions. So here I listed 5 most recently very important in that direction. One is high-dimensional Peakons. Today I'm going to introduce the still most likely is 1+1, some is 1+2. But for high dimension Peakon models, still very few in the literature. Yeah, of course, the computation makes that very hard. So I thought machine learning probably can help us to do something. Suppose you have some initial data. The other thing is describe the Peakon system, as I know some people work on in the literature, but it's still far away from a Lux pair. I mean the integrability in Lux pair for Peakon system, we didn't find that yet. So I put down here, probably we're going to use deep learning. One of the things is here's analysis for two-dimensional integrable Peakon system. This is for people doing analysis work, okay? So 1 plus 1 dimension integral Peakon system, it's a lot of work in the literature. But for the 2 plus 1 dimensional system, is recently some people work on, but still very few models, okay? The fourth the problem is from Peakon system, this actually eigenvalue problem, okay? This is for pure mathematician gonna do. Today, later on, I'm gonna introduce some high order Peakon models. This is high order for differential order, it's not for nonlinearity order, okay? Some more details, you can see my work in my web page and ResearchGate. This is the research projects in my group. Before go to my regular formal talk, now let me introduce my PhD program in our school. So our PhD program is not in traditional math. It's called MISEA. It's mathematics and statistics with interdisciplinary applications. So actually here I put down 4 applications. One is for using computational math or applied math with computer engineer or electrical engineer. So one of the directions I mentioned earlier, how do you use inverse problem from mathematics to do the image reconstruction? Okay. Second is math biology and nonlinear mechanics. Third is data analytics and medical application. Then mathematical physics, there's a traditional solid wave and the integrable system would be in that category. Now, for students, very important is, we offer the financial aid is something like 26K regular semester, this 9 months. Okay, now summer separate. Okay, and the deadline is March 1st. So for the program, so if the students enter masters, that's just the 3 years. If the enter with bachelor, maybe 4 years. Okay. If any questions, then you can, after my talk, you can talk to me. I'm the person in charge of our program. Okay, now go to the formal talk. In my talk, I'm going to talk about, the Kamasa-Home equation, single Peakon, and more Peakon models, and then most important recent work for the high order model and the integrability. Okay, I say again, this high order for the differential order. It's not for nonlinearity order. All right, let's start from fundamental things. Yeah, I don't know the audience, the students more or faculty more, but anyway, this part will be very fast since most of you know that classical solitone from KdV equation, that's permanent form of the traveling with setting, and the stable, is use analysis work as the interaction for on solitone because that's integrable. That's classical solitone. Now, interesting things you might in the literature is Peakon. That's 93 by Kamasa and Home, right? Okay, so Peakon is peaked solitone. Okay, which means if you use the graph to describe, which means at the crest point is continuous but not smooth. So both left and right derivative exist, but they are not equal. Okay, that's called Peakon. What is the mean cusp point? Cusp point, which means at crest, the peak point is going very deep. So something like this. Okay, there's at that crest point, you see that the left derivative and the right derivative both not exist. Okay, so in other words, the derivative has infinity jump, that's for custom. If a finite jump, that's for Peakon. The integrability in my talk, this in the sense of Lux pair, just clarify that, not for other sense. Okay, now I'm gonna briefly recall what is the first paper to do the Peakon. Actually, if you check the literature, you will find this paper by Thornberg and Witham. And put down the green, the blue color. Published in 1978. Okay, numerical and theoretical study for some nonlinear wave phenomena. Okay, the model they considered is following page. I just copied from their paper this model. Okay, this model looks like there is some relationship to Hunter-Sexton equation or some other equation, if nu equals 0 or something. Okay, but not right moment we talk about that. Okay, in general, this equation is not integrable. Okay, but they still have some solution. Look at the solution, the equation 31. How does it look like? Those coefficients are very exact the number there. This is 1.5 nu. Nu is what? Nu is exactly the amount in the equation, this number. But traveling with speed is very specific. So in other words, so this is unique, the solution. But in that paper in 1978, they didn't call this Peakon, whatever. They just explicit solution to the number 29. So later on, the people found, oh, this is, you see here the form. It is the Peakon, it is a peaked solid solution for number 29. So that is the first paper to do with Peakon, okay? But it's only single, because the wave speed is fixed already. So you don't have interaction at all. Now, what is the first model? The first Peakon model, but it's integrable. So that's Kamasa-Home equation. However, that Kamasa-Home equation first paper include that Kamasa-Home equation is by Foucault and Foucault-Steiner, the physical D paper, 1981. Okay. Moreover, actually, it's the fork model, or some people call them modified Kamasa-Home equation, is also one of special case. One of the special cases in that paper, you take some very special parameter. Okay, but in that paper, unfortunately, of course, they didn't study the Peakon and even didn't give the Lux pair for Kamasa-Home and the fork equation. Okay, let me show you that paper, how to derive the Kamasa-Home and a fork equation. So this is a copy from a physical D paper by Foucault-Steiner and Foucault. You know, this is typical procedure use a recursion operator, 30A, 30B in their paper. The Kn, you know, so equals phi is operator listed on the right-hand side. Now for first one, produce KdV, second one is an MKdV. Now this one exactly produce Kamasa-Home equation. Of course, you're gonna select special parameter alpha and beta and gamma, okay? So this CH would be special case of 30. This guy, you select alpha, beta, and theta equals some others. Oh, unfortunately, this would be inverse. So this is exactly fork or modified Kamasa-Home equation. Okay. All right. That's the literature regarding the model. Okay, now let's see the Lux pair. In 1993, you know, the Kamasa-Home equation attract a lot of attention because it has peaked soliton, right? It also has Lux pair that people already know. But analysis work by those people, I just leave some there. You know, in integrable systems, one of the algebraic geometry solution I did in 2003. Okay, let's see. There's why that Kamasa-Home equation is one of you know, special case Navier-Stokes, Navier-Stokes alpha model. But in their paper, they derived the Kamasa-Home equation use Euler system. Okay, if you look at the physical review letter paper. Okay, But here, when I was in Los Alamos, that's my first stop in the United States, in their Holmes group, worked on the turbulence. So one of the famous model is called Navier-Stokes, which is shown here. Okay, V is velocity, that's convection term. This is pressure, this is viscosity constant, this is Laplace, now this external force. This stands for the flow is incompressible. Of course, a three-dimensional Navier-Stokes is $1 million problem, right? Yeah, still holds on there, it's a long-standing problem. Now, there's some methods to study the Navier-Stokes. One of the important things, they just use this filtered velocity. Okay, U is called filtered velocity. Now plugging back to the equation number 1 and 2. So those Navier-Stokes alpha model. This is a turbulence group in Los Alamos. That's I think 2002, around that year. Okay, almost 20 years ago. That was when I worked there. When Derek was there as well. Okay. We is called an NS alpha model because you're going to introduce alpha. Look at this exact Helmholtz operator, right? Okay, plug in there, use the regroup the equation 1 and 2, you have following equation, this one. Okay, now we consider a very special case. Now, of course, this U is called a filter velocity. Filter, which means a filter by this operator, 1 minus alpha squared Laplace, okay? All right, for equation number 4, let's think about a very, very special case. No external force, no viscosity, no pressure, just 1 plus 1. This is a very special case. Now get what? That is exactly Kamasa-Helm equation. Okay, now this is of course 1 plus 1 dimension. So people work on the high dimensional Kamasa-Helm equation. How do you create? My suggestion is, still follow Navier-Stokes. Follow Navier-Stokes, so it has a physical background, but then put a Helmholtz operator like that. Now reduce from number 4. They consider 1 plus 2. Unfortunately, the 1 plus 2 in this way probably not integrable. That's why some people consider the rotational Kamasa-Helm equation may be integrable, okay, in somehow. Okay, so that is for background of Kamasa-Helm equation. So Kamasa-Helm equation has Peakons solitone. Of course, it's in traveling wave setting. Okay, if you put a traveling setting x cosine equals x minus ct, you plug in that equation, you will get such kind of a special solution. Careful here, this is the wave speed and that constant must be same. Okay, of course, at that point it's continuous, not smooth. But how do we verify that Peakons solution? So this is a purely differential equation. Now here, no different derivative. So you have to do something in distribution space. That's the Y weak solution comes out for Kamasa-Helm equation. Okay, because so most people are familiar with Kamasa-Helm equation. I don't want to see more detail how to derive. So actually, for students, you can do the homework. You put a traveling setting into there, you get how do you get such kind of Peakons solution? Particular Y is constant, C must be there, okay? For master students, it's good homework to do that. Okay. This is Kamasa-Helm equation. Now it's a Peakons solution, but the standard Kamasa-Helm equation at both boundaries goes to 0. So decay at both infinities, right? Now, what about non-zero boundary? Still standard Kamasa-Helm equation. So right now, many people work on the non-zero boundary condition, or called inhomogeneous boundary condition. Now, what about the Kamasa-Helm equation? Actually, we did 2006 with my collaborator. So the other person, JLNL, did a similar thing, but he doesn't focus on he has some other solutions. But our paper focuses on the solitary waves with the analysis work, okay? So for the non-zero boundary condition, which means a still standard equation, okay, no other constant or no other linear term on the left-hand side, still standard equation, but think about non-zero boundary condition. This is zero boundary, okay. Think about the non-zero boundary condition, you will get such kind of solution. Okay, this is a wave speed, but still traveling with type. Okay, this is what we did. Now analyze that solution, you can see at 0 is constancy because this is, the numerator, denominator goes to infinity. Of course, this is totally go to 0, now it's in C. At both infinities, you no longer 0, A equals 3C. Okay, the C is not 0. So that's non-zero boundary condition. Now at 0, actually, so Xe, okay, let's put Xe. At Xe equals 0, left and right, that's put infinity already. So the first order derivative at 0 has the infinity jump. That's why cusp comes out. Okay, that's one case for non-zero boundary condition. You have cusp. Now what about smooth solitone? Yes, we do. So that's why Kamasa-Hermann equation has a very good property, even beyond KdV. So KdV doesn't have Peakon, right? Doesn't have cusp. Okay, Kamasa-Hermann, has 3 kinds of solution. Okay, so Peakon, cusp, and regular smooth. Now here smooth solitones. Still, in our oral physics letter, we give such kind of explicit solution. Now so this boundary is going to this one. No question comes out. So what case you have the smooth solitone? What case you have cusp? What case you have Peakon? For Peakon, clear. Your boundary must go to 0. Now for the cusp and the regular solitone, it really depends on the ratio between your boundary and wave speed. Okay. As for what is the relationship, how exact amount there, now you have cusp and the smooth solitone. You should take a look at our paper. We have the detailed derivation and analysis, okay, on oral physics letter. Okay, that is for 3 kinds of solution. Now, since you have the 3 kinds of solitone solution, of course, you can think about multi-solitone. So regular solitone already did by some people. Okay, I know it's one of the Chinese professors, Yishen Li. Professor Li Shen already passed away, some years ago. And also for the cusp, he and his student did a similar thing. Now, what about multi-Peakon? Multi-Peakon by Kamasa-Hermann. Okay, I'm gonna show here. This is usually ansatz for the multi-Peakon. Okay. So the idea is what? This is the, ansatz of plugging the PDE, now reduced to ODE. Now you have how many unknown variables? 2, okay. So plug in there, those eliminate X variable, those produce just ordinary differential equation, but it's 2N system. Okay. So 2N system, you look at the right hand side, this would be sine function or signal function, okay. So look at the right hand side, you still have absolute value there. Of course, it's nonlinear, okay. No question. So because this is ansatz, so you do the PDE stuff, of course, you need to verify those variables make sense. In other words, you have to prove this system is integrable. Otherwise, your PIMQI doesn't make any sense, okay? Well, equation makes sense, so what we need to verify integrability for this ODE system. Now it's a 2N system, the ODE, we need to prove the integrability in the Liouville sense. First of all, you need to change it to what? Canonical Hamiltonian system. This is a beautiful formula by Kamasa-Hermann in 1993. This is the Hamiltonian. So this is H, and that's a standard. Okay, now prove the integrability for this canonical system. You need to figure out N independent quantities conserved, right? Okay, but how? So in the literature, of course, one way is you figure out Lux pair for this OD system. Now use Lux matrix, so you're gonna do determinant for the power function. Now you figure out all the consummation loss. Let's use Lux pair. The other ways for the finite dimensional system, you're going to use R matrix structure. Okay, a lot of things for finite integrable systems. Okay, what is it? The integrability was proved by Grande and his student Brodsky in 1996, published Physical A. Okay, when they proved the integrability for this system, that one, they assume, they put this condition. What does that mean? The Q1, Q2, and Q1, those are Peakon positions, right? So for NAT always like that, but the question is, if always like that, how the Peakon interaction? So their original idea is what? Is going to be use this condition to remove what? Absolute value. Remember, you have absolute value there. So remove that absolute value, then change the system to this. That's their work. Okay, under that assumption, now they got Lux pair. Now, of course, M and L, two matrices. Okay, M is antisymmetric and L is symmetric. Okay, those is just the matrix basis. Okay. All right. Since it has Lux pair, now you're gonna produce the conservation laws or the independent conserved quantities. Okay. So like I said, you just want to use the power, now use trace. Those of course definitely is conserved. Those form the independent and the evolutive functions, which is here. As per Liouville theorem, this system is integrable. But the question is, go back there. What is condition? Condition is here. Now question comes out. Can we remove that condition? That system still integrable under original one. There's no argument canonical, but under original one, still you keep your absolute value. Can we still prove the integrability? I didn't find it. Okay, that's a point. If anybody finds the such Peakon system will remove that condition, still integrable, let me know. Okay. Okay, that is the question open there. Now, think about why Kamasa-Home has the Peakon solution, why other not? So people always ask, so only Kamasa-Home type equation has the Peakon solution, or there's some other way to find a Peakon solution. Let me tell you the story for the integrable system. So actually, if you study the eigenvalue problem and the recursion operator, then find the Kamasa-Home equation actually from negative order. So far, all the integrable Peakon equation from negative flow of the integrable hierarchy, not positive. Okay, so let me show you a little bit. Since the time issue, I only have around 50 minutes, right? Okay, now let's start from eigenvalue problem. You're going to change the matrix form. This is easy work. Now you're going to figure out two recursion operator. I'm sorry, two Lanada operators. One is K, the other is J. So later on, the L equal J inverse K, that's called the recursion operator. The key number one, after you get this one, this is called a functional gradient. That's actually the earliest work should be by Professor Qiao, 1987 around, when I was his master student at Zhengzhou University. Okay, now this key things from this, the identity, not identity, from this relationship, okay. So suppose you have a number lambda, that is a spectral gradient with respect to the potential function. Okay, of course, the condition needs for M, either periodic or M decay. M decays at both infinity. Okay, now you have such computation. Okay, now, so number lambda knows now you're going to figure out the K energy satisfy this recursion, satisfy this the operator equation. We should see operator equation and find K energy. So for Kamasa-Home case, now exactly is those two operators. Okay, now you see that you can verify those two are Hamiltonian operators. Now produce a hierarchy, so you produce a hierarchy, of course, you need a source. Okay, the one source is from kernel J. Kernel J is here, J naught. Now kernel K is a third order operator. Of course, K has 3 seeded function, which I showed here. Those G sub K is a combination of those 3 seeded function. I use equation number 18. Now you're going to produce negative flow. So actually, this G minus 1, G sub minus 1 has 3 branches because you had 3 seeded functions. So negative flow, you have 3 branches. Okay. One branch is a special case. You put the other 2 coefficient 0, just keep the constant there. You exactly produce Kamasa-Home equation. Okay. This negative flow from Kamasa-Home equation. Now people ask, oh, what about you keep A1 equals 0, A2, A3 now 0? You could produce other equation, probably is integral differential integral equation or integral differential equation, but still integral because later on we show the Lux pair for the whole hierarchy. Okay, this is the Kamasa-Home equation from negative flow. Now, what about positive direction? Positive direction, you have another interesting equation which is called Hardim type, because it produces from the kernel of J. This kernel of J is M, this is 1 over square root M. Okay, you plug in the K equals 0, no J inverse. Of course, during the procedure, you have to figure out, by the way, have to figure out the inverse, J inverse and K inverse as well. Okay, yeah, because you need to produce the equation, you have to know the inverse makes sense. Now, positive direction, the first non-trivial equation is this. Put that constant equals 1, exactly dim type equation. This is also integrable equation. Okay, this is the way to figure out the hierarchy, for positive or negative direction. Negative is Kamasa-Home equation has Peakons and also soliton and Caspon. Okay, for this equation has Caspon solution. So if without second term exactly Hardim equation, yeah, what are they and his group people are going to work out to, Caspon solution for Hardim equation. Okay. Okay. I should add more stuff because show the Lux pair for the whole hierarchy, but if you show it's pretty long, I'm going to continue to show other scalar Peakon models. Okay, this is a whole story about the Kamasa-Home equation produced from negative flow and also physical background. Now let's see more other Peakon model. Okay, the Kamasa-Home equation, the coefficient is number 2. Okay, now 6 years later, so De Gasperis and his student Procetti, they're going to change number 2 to 3. They published this equation in the proceeding, I think at some conference in Singapore. Okay. Now this equation becomes very famous. The original that equation, we do know they derived the use of some Pahlavi analysis, right? Figure out some analysis property. Okay, like Kamasa-Home equation, of course, we can extend the whole hierarchy. Now for that one, I extended the hierarchy just 1 year after I did Kamasa-Home. Okay, that's called DP hierarchy and Lux pair. Okay, now since there's 2, 3, can we extend to any parameter B? That's exactly the Darryl and his student Stanley, his master student. No, I was there. I went to Los Alamos 2001. Exactly sometime exactly before 9/11 event. Okay, I remember it clearly. Stanley worked out, so for any, several kinds of B, they published. You look at archive paper. Okay, all the B family, but in the B family, only integrability for B equal 2 and 3. B equal 2 is Kamasa-Home, B equal 3 is De Gasperis and Procetti equation, but Lux pair given by those 3 people. So Darry, Andrew, and Professor De Gasperis. Okay, those are the third order eigenvalue problem. Okay, now the time part. You see here, you have lambda reciprocal. That indicates your equation for E equal 3 is also from negative flow. Okay, the power is negative. See here. Okay, now people ask, what about the positive direction? You need to look at my paper. This paper, I extended positive and negative, the hierarchy. Negative is dp, positive, there's the other equation in fifth order, but still integrable, okay? Okay, this is a story for the Peakons solution. For any B, actually, you know, for any B, this equation has such kind of Peakons solution. For any B, it is true. Now, nonlinearity is all the quadratic. Okay, now this, you know, it's a 2002 work by Stelly and Darrow. Okay, now people think about what about cubic nonlinearity? Still integrable, but with Peakon. So the first cubic model, cubic Peakon model, is this equation. Okay, when I did that one, this is 2006. I didn't know those three people already published a paper related to that model. Okay, now later on, people found, you know, so we cite this equation, and some people call it fork equation. And in literature, there's another model called modified Kamasa-Home equation. Let me introduce the other model, okay? Before doing that, let me mention this equation is still integrable. First Peakon model, cubic Peakon model, still integrable, and it also has the Peakon solution, okay? And also, of course, there's some solitary wave solution. Now, people, it's also called this equation, modified Kamasa-Home equation, I think since 2013. But this one, you know, called Kamasa-Home equation, modified Kamasa-Home equation, there's some relationship like, you know, it's negative flow from modified KdV equation. But in literature, there's another model called modified Kamasa-Home equation, which is this, by Goika and Reyes. Do you have any questions, please? By Goika and Reyes. This is published 2010. This equation called modified Kamasa-Home equation. Why? Because remember, KdV and MKdV, there's Muller transformation, right? That's called modify by Muller transformation. Now their idea is not going to find, so Kamasa-Home equation already there, not going to use a Muller transformation like this. Then this equation goes back to standard Kamasa-Home equation related here, but there's a linear term, but doesn't matter, still Kamasa-Home type equation. So that's why this equation much earlier than the fork equation called modified Kamasa-Home equation. However, this kind of equation number 40, probably no Peakon solution found yet, okay? So people are going to do analysis. Is that equation, this equation, I call the MOC, in order to distinguish in the literature, the people called modified Kamasa-Home. So actually we should make it that clear. You know, this is called modified Kamasa-Home equation. Now it doesn't have Peakon, but not proved yet, okay? All right, so there's this one has Peakon, but it's, you know, it's related to some modified KdV equation. That's people why they call it modified Kamasa-Home. Say again, I prefer those number 40 to be clarified. Number 40 should be called the modified Kamasa-Home equation, okay, by Muller transformation. Okay, you see here, the last pair for the cubic equation, the number 39, which is this. Okay, this last pair. You know, similar things, because you have the recursion operator for the fork equation, now you can produce the hierarchy. That's in the 1 year later, I published a little bit longer paper, 2007. Okay, that's called the hierarchy. But of course, that's in that paper, I don't call this hierarchy. This is just called new hierarchy. Later on, some people call that. And this hierarchy, there's some transformation and a relationship to other hierarchy. That's by Dr. Kang and others in 2015. That's in the negative flow is called that cubic Peakon equation. Okay, this one is still in negative flow. Now, what about positive flow? The representative for positive hierarchy, the fork hierarchy, is this equation. This is still integrable. When I check the literature, actually, this equation comes out from Professor Qiao and Professor Geng. It's in the 1991, much longer time. Okay, so this is very interesting. Okay, this is a story for the first cubic. Now, second cubic model, second cubic Peakon model is Novikov model, which this. That's 3 years later. Okay. But the difference between the first cubic and second cubic, first cubic, is this 2 by 2 eigenvalue problem. This guy is a 3 by 3 eigenvalue problem. Now, so what about lambda, the eigenvalues distribution? Yeah, but what about so the lambda, how to distribute eigenvalue lambda? Okay, is it real, all the real, or all the complex, or both? Okay, we don't know that yet. Okay, but that's for the pure mathematician working on the spectrum distribution. Next model is like a Gardner equation combination with PDV MKD. Now it's a quadratic, the Kamasa, cubic that's modified Kamasa work fork equation, then plus linear term. We call the linear term linear combination of those nonlinear terms. This model. This model, when you check it, there's you see here, Foucault's paper, 1995. That's a physical D paper. When Dr. Qiao did a postdoc with me and another professor, Jibin Li, we worked together for that equation, found the Peakon solution and other type solution. Okay, particularly for multi-Peakon solution. And the weak kink solution also comes out for that equation. For this equation work, we can put one particular talk to talk about more detail. I just give the information. This equation contains a lot of information regarding the weak kink, and weak kink interact with Peakon solution. Okay. Now for K2 equals 0, no quadratic term, that's cubic term, linear term. Also, my former student now is in Harvard University. He worked in 2011 when he did a master with me. Now worked out an explicit solution for the particular case K2 equals 0. Okay. Now so it has Lux pair for the whole piece number 45. The Lux pair for these two parameters are very different. Okay. When B not 0, this U alpha equals this. Look at the eigenvalue. It's square root inside. You see here. Okay, and this is restricted by number B. The A, capital AB, that's related or still in the negative direction. In other words, our Peakon model number 45, when B equals 0, you have Peakon, okay? That's still from negative flow. For number 45, I put some questions because of that equation has very specific, here, very, very peculiar, the Lux matrix. No question for the eigenvalue distribution. We don't know that yet. So B equals 0, though you get the Peakon solution. But B not equal 0, we get a weak kink solution, just like I mentioned earlier. That's Dr. Qiao and myself worked in 2012. So integrability for the unpeakon weak interaction solution for that system, the integrability didn't provide yet, okay? We didn't prove that yet. Okay, that's from the linear combination of those nonlinear terms. The other model is not for, as we mentioned earlier, this is for negative, for positive flow from a Kamasa-Home equation. So negative give Kamasa-Home, the positive Carradine equation we mentioned earlier already. Now let's come to 2 + 1 dimensional integrable Peakon models. If you look at the literature, these two, experts, Estesev, Chavez, okay, as Prada, they mentioned, holograph transformation for Kamasa-Home in 2 + 1 dimensions. Okay, it's published JPA 2005. This is their model. So if you do look at the next equation, just look at the first, it is exactly Kamasa-Home type. But only thing, second one, right hand side change the variable, right hand side change to y. If keep x, this goes back to Kamasa-Home. Now if keep this y, then you produce 2 plus 1. The idea is just here change to y. Of course, as per that idea, you can produce hierarchy. This is the hierarchy. Okay, this is still integrable. There are some Peakons solutions. Yeah, there's a lot of details in that paper, that 2005. And Dr. Shan and myself, they're going to work out our cubic term, this quadratic, this equation, no linear term. Now, so, but the question is, this here is changed to my, not mx. If you go back to mx, they'll go back to earlier model. Now, the change here to y, that's a 1 plus 2 dimension. Okay, what about this model has Peakon solution? Yes, my students, so 2 students, there's a Chinese student, there's a local student, they work together, 2017, they figure out some special solutions that use weak kink peak interaction solution for 2 plus 1 dimensional Kamasa-Home equation. Okay, but the integrability for the unpeakon system for this 2 plus 1 dimension still not provided yet. Okay, we didn't prove that yet, integrability. Okay, now use the last 15 minutes, I'm going to talk about our recent work, high order Peakon models in scalar form. Okay, one model, the high model is here. Okay, this is still Kamasa-Home B family type, right? Okay, now if m equals 1 minus alpha, that's a filter once, filter twice. If beta equals 0, now go back to B family. Now gonna filter twice, not filter once. Remember, the earlier in their original work, that's called the filter. Okay, filter 2 different parameters that we should have somehow your peak point would be smoothized. Okay, alpha, beta, of course, the product not 0. Some analysis work already done by Zhu and other professors. Okay, now for the Peakon, actually, for work done, because you filter twice, so single speed we'll see. Well, I found this one. This is one. This is a Peakon solution to this equation. Okay, 2 different parameters. When draw the graph, actually not exactly like a original Peakon. That's why I call it pseudo Peakon. Why? If you draw the graph something like this, you see here, it's both sides. Now when x goes to infinity, still go to decays. But at that point, it continues to second order derivative, no third order derivative. So we can see the smooth until first order derivative continues to second order derivative, no third order derivative. Okay, that's why we call it pseudo Peakon. So you have 2 terms. Usually you have just 1 term. Now why here 2 terms? Because you filter twice. No question comes out. Can we filter the 3rd time? Yes, of course. You just add more term. Can we filter the finite times? You just put a sigma or something like that. Okay, it's still pseudo Peakon. Pseudo Peakon, but it's 1 speed. So single pseudo Peakon. Can we do the multi pseudo Peakon? Yes. This is also I think probably here I didn't put the formula here, but we already did. That paper published by my visitor, the Professor Liu. This is from Inner Mongolia University, 2018 Journal of Nonlinear Mechanics. Okay. Okay, and that is for the high order, actually 5th order Kamasa-Home B family model. Now for Novikov, we can do similar thing, but this cubic things comes out. Okay, there's M still same as before. Now question for those B family, Novikov and B family, Kamasa-Home, those 2 equations, we didn't prove integrability yet. Okay, in other words, we didn't find the last pair for those 2 equations yet. Even B equals 2, Okay, but m equals that, okay, for different alpha and beta. Okay, even b equals 3 in this equation, the m equals that, we didn't find Lux period. But they do have what? The pseudo Peakon, okay? Now this is for the B family Novikov equation. Okay, it's upper and down. So those two B family pseudo Peakon equation, we didn't prove Lux period. But do we have a Lux integrable, but still with those pseudo Peakon? Yes, we have an example. That's our recent work. Before doing that is a B family fork equation we still consider, but no answer yet. Now is our recent work, and let me show you. This recent work with Reyes, and okay, the idea is based on the model. The 3 people, Reyes and his collaborator, published in 2015. The equation of Kamasa-Home type and geometry of loop groups with some geometry background. Okay, I think it's they studied Cauchy-Kudasi equation, then figured out that equation uses zero curvature form. Okay, the original paper, they put this long equation. I do like that. They're going to put concise form. I rewrite that form in this way. How do we understand that? That is exactly Kamasa-Home type. Okay, but what is the relation between M and V? So M equals V, you can write down 1 minus square. Now V equals that. Now so what? Exactly 1 minus d squared, not square U actually. You plug in there and go back to that equation. So rewrite the in the concise form. So actually this is a 5th order Kamasa-Home equation. It is integrable. It has Lux pair, this showed earlier. Okay, does it have a Peakon solution? Yes, I'm going to show you. This type still pseudo Peakon. This is new type pseudo Peakon. So usually without that term, usually know this term, just the here, C over some constant exponential. Now for this one, we have extra term 1 plus psi. Okay, this is our recent result. This is the pseudo Peakon. You can plot the picture. You figure out the first order derivative and second order derivative. So smooth to first order derivative, continue to second order derivative, no third order derivative. So this form is not hard to compute, very easy. Okay, this is the pseudo Peakon for the 5th order Kamasa-Home equation, but it's integrable. Right now it's integrable. Can we do the unpseudo Peakon? Yes. So this is unpseudo, we already figured out. The format is PI, it's a little bit different from the standard Kamasa-Home and other type. There's a PIT and there's exponential, you have that tail term. There's multiple. Okay. So what is the PJ and the QJ satisfy? The satisfy canonical Hamiltonian structure that exactly goes back to, this guy goes back to standard Kamasa-Home equation. That's very exciting. So connection, so here between pseudo Peakon and Peakon type. Okay. Does it, have finite conservation laws? We didn't, the integrability for this system, this should be integrable, okay? But I'm gonna show you n equals 2. What about 2 pseudo Peakon interaction? Very interesting phenomena for n equals 2. When we figured out n equals 2, this is in the system 2 ODE, okay? For P1, P2, Q1, Q2, okay? For ODE system. So comes out from this H, n equals 2. Okay, solve this P1, P2, Q1, Q2. Exactly, you have this form. A is any constant. Okay, so plugging back to here, U. Now you get such kind of the explicit solution. There's 2 Peakon pseudo, okay, 2 pseudo Peakon solution. Okay, now of course, if you have an explicit formula, you just take a special number A you can plot. So this is here, I put a very special case now, to see clearly, now the put the A, so
Excuse me, Professor Qiao. We cannot hear you.
Okay, let me reshare. I don't know. I have no idea about it. I don't know why it's lost the direction. It's no connection. Lost the connection, right?
No,
Oh,
no,
I
just
see.
the
So
sound.
your connection was unstable. Okay.
Okay. So just the last part, right?
Yes.
Yeah, just last part.
Let me see. Okay. Is it here?
No.
Here.
One more page. Yes. Yeah. From here.
Okay.
Okay.
Yeah.
After
Yeah.
from
For this
164.
part, remember, interesting
Yeah.
thing. Okay. All right. So interesting is when you solve this two pseudo Peakon system, you get P1, P2, Q1, Q2. You know, it's a hyperbolic cotangent. The other way is log cos. The A is any arbitrary constant. But you know it's here. The important thing is the second part here is minus. This is important. This is science important. Doesn't work. Yeah, this is the important sign. Because of that, you see here, I put it, you know, it's selected, you know, the different, very specific constant. Make sure this A/2 is 1. Thus, I want to make it a concise formula, want to plot. For others, you know, the constant would be similar picture. This is, you know, is a 2-dimensional figure for this solution. It's going to be from this one, no upper. But the travel is not like that. Okay, travel not like a regular solitone. Why? When I put to the 3-dimensional, you know, for the 3-dimensional picture, this like this. Okay, this horizontal is x, this direction t, this vertical is u. Okay, when the t from negative close to 0, now you see here, your amplitude starting from here gradually to 0. When close to t equals 0, suddenly crashed, suddenly goes to flat, both sides flat, goes to 0. Because why? Because you look at the formulation, you see here, look at it. When t goes to 0, of course, this guy is what goes to infinity, right? But inside of that part, because here's minus, this goes to 0. That's you can use L'Hopital rule to easily check. That's t uxt when t goes to 0, this red solution goes to 0. So that's why the picture. Actually, this picture, I asked Professor Low. I don't know Professor Low is on the meeting or not. You know, but actually, I asked Professor Low to help me to figure out. He's an expert in Maple, so draw this graph. You know, I draw it only for this 2-dimensional, but I need this 3-dimensionals here. It's here from this goes to gradually 0. Now, from positive, from 0 to 5, now so gradually from 0 goes up. Now, so you see here, your amplitude is gradually come bigger and bigger. Okay, so you put all the time from minus to positive. There's a cross 0. There's something like, you know, from negative goes to 0, no 0 to this. The other part is going down, down. Okay, not like a regular solitary interaction. It's like something, this part is negative, then go the other part go positive, not the interaction, something like that. This is a different phenomenon for the pseudo-Peakon interaction. Okay, I think it is done for the talk, but before I finish, I put some open problems. So for the fork or modified Kamasa-Home model is integrable for the, the pseudo-Peakon interaction. The integrable one not so high dimensional, okay, high order, not high dimensional, I'm sorry, high order differential. This means differential order, not a nonlinearity order. Is that integrable? We don't know yet. Now, pseudo-Peakon stability, I didn't see any pseudo stability proof yet. For Peakon stability, we saw some people already did. This is analysis work. Okay, we need to do collaboration with those analysts. Okay. High dimension Peakon, so I mentioned earlier from Navier-Stokes, we produce a 1+1. Can we produce 1+2 from Navier-Stokes? But we need to look for integrable. For the discrete Peakon system, integrability, the integrable in the sense of Lux pair. That's part actually when Professor Dajun Zhang visited me, we worked on the discrete APIOS, but finally we didn't get it. Okay, we still think about it. This is hardest part for discrete Peakon system. Okay, so first of all, for discrete Peakon, I think most of the cases our functional space is not well defined. We need to extend somehow. Okay, analysis for 2+1, there is some work already. People are going to do generalized 2+1 Kamasa-Home, then put it back to rotational Kamasa-Home. Last part is eigenvalue problem stemmed from the Peakon system, but for the eigenvalue distribution, some we know, but some we don't know yet. I think that's pretty much for my talk. Thank you so much for your attention.
Thank you, Professor Qiao, for your wonderful talk. Any questions? Any questions?
That's maybe a small question.
Okay.
Yes, go ahead, please. Now
Okay,
I go back to normal.
This is Giorgio speaking. So so you showed the model of Gorka and Reyes, and yes, it appears to be connected to your filter option. But when you actually take alpha and beta to be the same, and so it generates this sort of
integrability.
You call it like a resonance solution. So that's why you get this linear term. Is it correct, or?
Mm-hmm.
Because they look quite related to me, at least.
Yes, that's actually based on their work. We worked on the 5th order. Notice regular 3rd order, not the Mach equation, but it's a 5th order Kamasa-Home equation. Let me show you that piece. Let me show you. You're asking that equation. You're right here.
Like it's 61.
This is another real curvature formula.
Mm-hmm.
Those also, if you write down this, people are gonna say, oh, this do like. Okay, I'm gonna rewrite it in the good formulation. Those you see here. This you are right. Alpha equals beta. In this case, you go back to the 5th order earlier form. You see if alpha equal beta, then go to this form. Alpha beta equal 1. Actually.
1, exactly.
Yeah, that's good, Giorgio. You're right. Now, so remember the earlier one. I think
so when you show like the solution, exactly like 54, if you assume that actually your alpha and beta are
but be careful here.
If you take the limit form, of course, you will have some linear term dropping out from taking the limit.
That's very good question. So you see here, alpha, right now, why we don't require alpha not equal beta? Because in denominator.
Yeah.
Now you're going to see here, maybe alpha goes to beta. Consider that limit.
Yeah, that should have some form of limit, I guess.
Right, we can compute that limit. Let me see. If alpha goes to beta, that's of course, there's something else, okay? But this is goes to, the denominator goes to 0. Let's say numerator goes to 0 as well, definitely. Yeah, those two terms same. Now you're gonna use the L'Hopital rule again. I don't think we can get the form something like this one. You want to see that formulation is the limit case, right? That's your question, right?
Yeah, that's my question. Yeah, exactly.
Okay, very good. I guess, you want to see this part is going to be the limit of that case when alpha goes to beta.
Yes.
Okay, so I will check that, but momentarily, probably, I'm not sure yet. Okay, we can check the limit.
Okay, thank you.
Okay,
Is
good.
this equation with some Hamiltonian trick?
Which equation?
The last one, the high order.
The high order one?
High order, yeah, the high order command form.
This one?
Yeah.
This one?
Yes.
That's what Giorgio asked.
Yeah.
For this one, so it has, it's called a pseudo Peakon, non-regular Peakon. Okay. And it also has Lux pair, that's integrable. It also has un-Peakon system, that actually is called un-pseudo Peakon system. The question is,
can this equation be derived from some Hamiltonian trick?
Hamiltonian trick, okay.
Hamiltonian. You have three, for example, you have 3 Hamiltonian operators, and then you can reorganize that, rearrange them, and then you can derive this equation, like from the Hamiltonian operator of the KDO and to derive.
Oh, you mean, okay, from K over J, right? So something like this, the Hamiltonian structure, right?
Yes.
That's very good. Actually, I didn't talk about the Hamiltonian structure and the conservation laws. It's Reyes right now. That's my collaborator. He's working out by Hamiltonian structure conservation laws for this equation. That's good.
Okay. Yeah.
Yeah. This
okay,
but this that's the new result. We didn't publish yet. You see. Yeah, this is my part. I finished my part. Reyes still figure out like this equation, the local conservation laws, Hamiltonian structure derived from, like you said, a lot of things. So this is for integrability properties. But the big issue is, like I said lastly, is pseudo Peakon stability for this equation. Nobody proves yet. That's important. Yeah.
Okay, so I think it's time to close this.
Can I stop share?
Yeah. Giorgio?
Yes.
Giorgio?
Yep.
Yes.
Exactly.
Okay,
So I think we can thank the speaker again and all the attendants. And we will be back in 2 weeks' time with another talk by Nobutaka Nakatsuno from Tokyo University of Science, not of Marine Science. Well, I never recall the Tokyo University of, I think, Agricultural Science, or that's long name.
Yeah.
So thank you, everybody, and I will close the meeting now. And have a nice day, or have a nice evening, depending on your time zone. Bye.
Thank you, Giorgio.
Bye.
Bye.
Bye-bye.
Bye-bye.
Bye.
Bye-bye.